to the cloud. Okay. Right. Take them there. Come on. Yeah, I think we got it right. Almost there, and I can't see that. Any questions so far on error detection?
Which is actually CRC and Hamming. Well, when would CRC be better?
When Hamming code is better.
So when would CRC be recommended over Hamming code? Hamming code specifically tells you where.
Hamming code is great if there's one bit error. If there are multiple bit errors or many, it's very inefficient and very slow and all those things. So it's not actually used in computer networks because you're never sure how many bits you're gonna have, how many bits are gonna flip. And therefore Hamming code at the moment as is not really used on networks. It might be used somewhere where you might be certain there's only one error. It'll be great. But the fact that in networks we can never be certain, then there could be any number of errors, and that makes it very inefficient and very slow. Okay, let me just see what did we do. I keep a note of what we cover. Oh no, that's different. We did parity, we did, Hamming code. Is everybody okay with Hamming code? Right, so the last one that's left, we did parity, we did block parity, we did CRC and Hamming code, and the other one is checksum, number 5. Checksum, right? And this is used a lot on the internet. It's used a lot on the TCP network. As you probably know, the internet, when it started, the internet protocol that operates at level 3 or layer 3 of the communication. If you are aware what layer 3 is, anybody knows what layer 3 relates to? Let's start with layer 1. Well, yeah, layer 1 deals with signaling, just bits and signals, electric signals, light signals, whatever. And layer 2 relates with communication between neighbors, any directly linked machine. How do you exchange information with your neighbor, with a machine that you're linked with? Then level 3, how to pass information to other machines you're not linked with. So it goes, no, this is called network layer. So routing, how to deliver a message from one end to the other end, so it knows about the network. This is the one this is the only part, or the only part of the communication system that deals with the network. The data link, that's layer 2, only deals with the first machine, the nearest machine to you. Wherever you are, if you're in the middle of the network, it only deals with your immediate neighbors. But layer 3 deals with the other end of the other machine, so it finds the best route. That's where we do datagram switching technique and virtual circuit switching technique. That operates at layer 3. Anything to do with the network is layer 3. And then layer 4 is end-to-end. Forgets about the entire network, just talks to the final machine. Two end machines communicate together. Called end-to-end communication. So the internet protocol operates at level 3. The datagram switching that the internet uses, it deals with layer 3 and it delivers information, but it doesn't provide any error detection or acknowledgement. So and they realized that was really bad. It's not a great quality or any great technological kind of advancement just to deliver data, but without any acknowledgement or error detection, as the other networks were actually providing the virtual circuit-based networks. So they introduced an error detection between end to end at the next level, which is, you can call it transport layer, or you can they call it TCP layer. So at TCP layer, we provide error detection. And on the internet, at TCP, they use the checksum error detection system. So it's used a lot in today's networks on the internet. But they don't do error check on the entire network. They send big packets and they travel. They only check the headers of the packet. They don't bother with checking. They still don't do a full error detection on the data itself. But it's used a lot, and it's good to know about it. Okay, good. Right, so how does it work? It's quite simple. The idea is you just add, it says the sum, that's summing up all the data, all the bytes, and then at the end, you find out, replace the sum with some complement number. We did pretty much the same with CRC, but I'll just explain it in very simple terms in using decimal numbers. Imagine if you're sending the following data. Imagine, maybe say 44, maybe 30, that makes it 74, and then another 20, that's 94, and 16, maybe 16, right? Imagine these are the numbers we are sending. So if you add them up, 44, 30, 20, and 16, they come up to 106, right? Or am I wrong? No, 110, yeah. If we say our maximum number, for example, is 100, so let's just see what would complement it. Let's divide it, take the remainder, which is 10, and what would bring 10 to be complemented to 100? And let's say they say 90, so that's what we add. So the idea now, that's now not part of the data, but that's the sum that we send. So it's a complement of 10. Just like on CRC, we send the complement of the remainder based on, some divider. Let's say the divider here is 100. So now the receiver counts all these, sums all these numbers, including this, and that should come up to a number that will divide by 100. It'll probably come up to 200 or 500 or 700 or whatever it is. Now if he's divided by 100, it will have a remainder of 0. That's the basic idea again. Right? It sounds a little bit too much, and then you have to do division and you have to get remainder, but it's really none of that happens because it's binary. It makes it a little bit easier, and they use something called one's complement addition, which is very easy. It's a logical operation, and it always, it's instead of adding, we do the one's addition, one's complement addition. So it's very, very fast, and it seems to work. So let's see how it's done in binary, and you need to know how it's done. Like it's like you need to know how Hamming code is done by a sender or receiver. How does it actually work? And you need to know the calculation. There's definitely exam question on an error detection system. So there'll be one or two of them. You know, here's a problem. Does this frame contain an error? You're a receiver, or you're a sender, and here's the data. I will return that thing if I find it. It's gonna start ringing sometime. Oh, there it is. Now, right, so the way it works, let's take a frame or a packet, and let's act as senders and then act as receivers. See how this thing works. Imagine this data, 0, 0, 1, 1, 0, 1, 0. That's 1 byte. Here's another byte, 1, 2, 3, 4, 1, 2, 3, 4, and maybe another byte, 1, 2, 1. Here's a frame. This frame can be 3,000 bytes. We just take 3 or 4 and we work on them quicker. And the idea is to add them up together. Add this byte, byte number 1, this is byte 1, byte 2, I'll just mark them here. So now I'm gonna have byte 1 plus byte 2. So I'm gonna take that byte, bring the other byte under, I'll just put them underneath one another. Easier for us. Everybody knows how to add in binary? You probably did it in first year, and you probably forgot how to do it, but it's easy. I'll remind you. So let's add up in binary. Any time you add two numbers in binary, they're either going to be 2 zeros, 0 plus 0 is 0, or a 0 or a 1 and a 1, or 1 and a 0, the result is 1. But if it's 1 and 1, that's when you might have a bit of a problem. So I'm just going to tell you what 0 looks like in binary written. That's a 0 in binary, right? So I'm just gonna write, that's 0. 1 looks like this, 0, 1. That's how to write 1 in binary in 2 bits. 2, how do you write 2 in binary?
1, 0.
Yeah, thank you. And 3, anybody has 3? 4, okay, we don't need to go any further, but just for fun. How do you write 4 in binary? 1, 0, 0, right? The first bit always has the value 1, this one has the value 2. So 2, there it is. And the next bit has the value 4, and that's how we write 4 in binary. So the first bit always has the value 1, 2, 4, 8, and so on. So it's easy enough, but we need to know how to do it. Now, right, who's going to help me now? At the very end there, you look like you're very interested in this. So tell me, what's 0 plus 0?
0.
Please, thank you. 1 plus 0?
1.
Thank you. 0 plus 0, I know that. 1 plus 0 is 1, right? 1 plus 1?
0.
Yeah, well, it's 2, and that's how 2 is written. A 0 and a 1 in the next column. So we write a 0 here, and the 1 we put in the next column, we say we carry the 1 with us. Right, so you write the 1, the little 1 on top of that column. There it is. Now, 1 plus 1
0.
is another 2. So a 0 is written here, and 1 is carried forward. 1 plus 1?
Same again.
Same again, 0 and 1 there. Now, 1 plus 1 plus 1? 3, and that's how 3 is written. So it's 1 here, and 1 in the next column. Right, that's why it's handy just to know this. So now, this was 8-bit turned into 9-bit. We call that overflow. That's how one's complement works. It says, if you get a 1 flow, only if there is an overflow, put it in, add it to the rest of the bits. So get rid of it, remove that extra bit, the 9th bit, and add it. So it's added. So 0 plus 1 is 1, and the rest of them 1, 0, 1, 0, 0, 0, 1. That's it. So that's adding the first 2 bytes together, byte 1, byte 2, using 1's complement. Now, let's bring add the next byte. And you just keep doing that till you reach the end of the frame. So the next byte is 0, 0, 1, 1, 0, 0, 1, 1. Okay, you can give me a hand here, please. 1, 1.
2, so 0, carry 1.
Yeah, and this is 3.
1, carry 1.
1 plus 0, 0, plus 0.
1.
1. And 1, 1, 1, 0, 1. And there's no overflow. So you don't add another 0, another 1 to the byte. If there was a 1 here on the left-hand side, you remove it and add it to the byte, and that's... Okay, so this is like the original user data. 44 plus 30 plus 20 plus 16 comes out to 110 or something like that. Now, we want to create the complements of that. So the complement of that, you just turn, I don't know what number this one is, but what's the complement here is, what is the other number that you add to this one that they all turn into ones or zeros? So the complement of this, just flip all the bits. A 0 turn it into 1, and 1 turn it into a 0. So this is 1, 0, 0, 0, 0, 0. What's that? 1 and a 0. And that's the one, the complement that will be sent. So now we take those 3 pieces of data and we add this byte at the end. And this is the complement of the sum of all the bytes in the frame. So basically, the frame is going to look something like this. The first byte doesn't change, 1, 0, 0, 1, 0, 1, 0. The second byte is 4 1s, followed by 4 zeros. And the third byte is 0, 0, 1, 1, 0, 0, 1. And then followed by the last byte that we have here is 0, 1, and then just 1 at the end. And this is the frame with the checksum. It's gone. Now, what's the idea in that? The idea now, if you add all these numbers and do a complement or convert, flip all the ones to zeros, you'll find you'll have lots of zeros. We'll see if it's correct. So let's do it. Now, what we've done is what the sender would do. Just add everything, flip the ones into zeros and zeros into ones, and that will be the checksum byte that goes at the end of the frame. Now, let's see what the receiver does. The receiver, all it has to do is just add all these together. And then flip the bits, and you should have the zeros. Now, remember, this bit here makes this number, it complements all these numbers to the maximum possible number. We'll see how it works. So let's do it. So 1 plus 1, 0, 0, 1, 1, 0, 1, 0, plus the next byte, which is 1, 1, 1, 1, and 4 zeros. Okay, who's going to take the credit here? You add these for me, please. And you follow, just in case we make a mistake. Yeah. 0 plus 0 is 0?
1.
Yeah? 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 Yeah?
This again. 0 and carry 1 again.
Yeah? And then? 1 plus 1 plus 1 is 3. How do you write 3? Yeah. You should know 1, 2, 3, and 4, and 5, how they are written in binary, but it's okay. Now, this is an overflow, so we just add it to this part here and we repeat. 1, 1, 0, 1, 0, 0, 0, 1. That's now adding those 2 bytes using 1's complement. Let's get byte 3, so that's 1, 2. Now let's add the 3rd byte. That's 0, 0, 1, 1, and 0, 0, 1, 1 again. Okay, keep going, go on. Yes, 0, and carry 1, that's 3. Do we add the 1 here? No, we don't have an overflow. There's still 8 bits. Right, that's done. Let's add now this. This is the last byte that really not part of the data, but it's just used to check the correctness of the data. So this is 0, 1, 0, 0, 0, 0, 0, 1. And that gives us 1, 1, 1, 1, 1, 1, 1, 1. It looks okay. Let's do the final flip all the bits, and you end up with, and as long as we get zeros, then there's no error. If any of these bits flipped, we'd get different results, and we'll say, the final bit doesn't go back to zeros, and therefore there's an error. So it's a simple system. It's extremely fast. I don't know how many errors does it or does it not discover. I'll leave that up to you to check it out. But this is, it's used a lot on the internet, on the TCP. The internet, when they got end-to-end and they decided to add error detection and acknowledgement, they left the older version with no error detection. They called it UDP, and they added those error detection and acknowledgements and call setup first. They call it connection oriented to the TCP. So really the internet at the next level, level 4, has 2 parts. Part just has nothing added to it. The other part, where they added error detection and acknowledgements. And they actually control congestion on the networks through that way. They use sliding window protocols. So this is the end of our error detection system. And now tonight, hopefully, or tomorrow, we'll put a tutorial, and you will get your practice on that. Any questions? Okay, I'm gonna stop recording.